Welcome to this new session with a theme which is perhaps somewhat obscure for most of us. It has been proposed by Steve, so I give him immediately the micro. And as usual, after the lesson of Steve, we shall have a Q&A session during which, of course, you can speak, ask questions, and so on. Steve, you have the micro on the screen.
Okay, let's just make sure that everything works on the screen. Um, so, and one other thing I have to find. So while I'm desperately searching, first, hello everybody, and good. Okay, got it. So let's go to here. Okay, so you can all see this now?
Yes, I can see it.
Okay. Okay, so far we've talked about some fairly extreme objects, most of which are intrinsically explosive, like supernova events, whether they're induced or not, novae, which are obviously induced by companions, but are intrinsic explosions, LBVs, and related very massive objects that undergo instabilities because of internal processes. Now we're going to be facing another class of objects. I thought since the LSST, otherwise known as the Rubin, is going to be coming online very soon, and there are going to be more alerts than currently deals with the imposition of new tariffs. The result is going to be a flood of requests and alerts to identify and classify the optical counterparts of those sources that are going to turn up in extremely large numbers. The individual identifications are going to be based on generally light curves, because that's what the Rubin is going to produce. But a good deal of it, especially in follow-up, for those that are going to be bright enough to sit in the observing parameters of your telescopes, will be requiring spectroscopy for identification and then follow-up. You know, something that we know already from the automated searches like the Zwicky Transit Facility and OGLE and Assassin, is that having a light curve and having the identification really isn't enough. You don't know the physics unless you can do the spectroscopy. It's the only way you're going to be able to tease out the multiplicity of processes, especially in sources like these. Something I've hoped by now I've been able to make clear, that without spectra, you are only able to interpret the spectral energy distribution in extremely schematic ways. You neither have the resolution nor the dynamics. The only thing you have is the energetics, and often not even that if you don't have the bolometric energetics. So this is going to be an example of one class of objects that will, I think, underline some of what we've been talking about. A lot of what we'll be covering tonight, a lot of the things I'm going to say will seem redundant, and I hope that doesn't get annoying. But once you're dealing with the radiative transfer and the formation of the spectrum, the processes that go into that are very much the same across this wide range of phenomenological subtypes. So there'll be a lot that's familiar here, and I hope that will both reinforce things and make you feel a lot better because you understand it all. Okay? So to start with, uh, one of the concepts that is really puzzling, uh, incredibly well known, and largely misunderstood is the idea of a common envelope. Uh, this is going to be very important for the discussion of red novae and mergers and even tidal disruption events. So I want to start with a class of objects that you know very well. They're called W Ursa Majoris stars. These are stars on the main sequence or extremely near it, below the terminal main sequence, that happen to be close enough together that they do something that's extremely antisocial. They kind of form a common envelope. And that term means that there's a photosphere that completely covers the two stars. Let me go to a diagram first. So change screens here. So, boy. Okay. So when two stars have a sufficient separation, one from the other, there may be, uh, in fact, there will be as they get closer, or as, excuse me, this is, I was getting ahead of myself. Let's imagine that they're born this way, that you have two stars that somehow wind up being bound in a binary system at a separation such that they're at some distance from each other that's still relatively small compared with their radii. And so across the star, there's a tidal term that the force on the two sides is obviously slightly different. The stars, if they're going to be stable stars, have to be in hydrostatic balance. And so the pressure gradient, that is the outward gradient of the internal pressure, has to balance over a surface which is distorted. And the result is, if you have ordinary stars that are well separated, that when they go into this kind of distorted mode, the temperature of the star is going to be different depending on which side of the star you're looking at. This is the same effect that you have in rotating stars, that, to use the example, so here we have the line of centers. I'll call this M1 and M2, and they're not necessarily the same, but these are separated from each other, okay? Now, if you have a star that's rotating, this is just to put this in perspective. The star is obviously going to take a spheroidal figure. If it's rotating slowly enough and we take the picture that it's like a balloon, then it's going to go to an oblate spheroid. And so within a, a given solid angle, the physical area covered by a cone is different at the pole and the equator. And the result is that if this star is going to remain in thermal balance, that is a uniform interior and a luminosity that has a zero net flux, so the luminosity is equal to the rate at which energy is flowing through the whole surface, the temperature that is reached at the equator is going to be lower than the temperature at the poles because of the relative area through which the radiation has to pass. The result of that is you get what's called gravity darkening, that at the equator, it's a little bit less luminous. The surface brightness is a bit lower than it is at the poles, depending on how distorted the object is. Now, this has an important consequence. And although this is just a single star and it doesn't seem to be related to what we're about to do, I want to make this clear that when you're looking at the pole, and this is the surface of the star, the effective temperature and the pressure are both going to be different than at the equator. The temperature will be higher and it'll look as if it has a slightly higher surface gravity. So the pressure broadening of the lines is going to be a bit different and the ionization is going to be different. That means that the same star viewed from the pole or from the equator will actually look different. And at some intermediate angle, you're going to get contributions from both parts of the surface weighted by the relative temperature, that is surface brightness, of that part of the surface. Okay? So far? Now imagine here that this is just in a binary system where one of the stars is rotating like mad, and the other star, for its own personal reasons, is spherical. And we look at this system at some angle. Then, or even imagine that this is an eclipse. As the eclipse is proceeding, different portions are going to be cut off. And so if you have a partial eclipse and you're just removing the equator, the spectrum is going to change because you're going to see the pole. If you happen to have something really bizarre and the star is orthogonally rotating to the orbit, and there are such systems, DH Hercules is a very good example of that. The same thing is going to happen in reverse. You'll see both the equator and the pole, but the pole may very well be occulted, and so you'll see the equator. In other words, never on this surface are you seeing a single classical spectral type in the sense of a spherical star as we're supposed to teach it in elementary astronomy classes. And I noticed that Chris Corbally is on the line. So, Chris, my apologies if I've misrepresented MK, but the since one of the standard stars happens to be Vega, and Vega looks like this, we know now. It's one of those interesting things to ask in this case, what would happen to the composite spectrum of these? But my point is, let's imagine that you have two stars like the sun that happen to be so close together that instead of simply being distorted, they actually form a kind of common mass envelope. What I mean by that is that this surface is optically thick and material is flowing around the two of them, which is perfectly allowed because there's a gravitational potential here called the Roche potential, the same thing we've been talking about for novae and for other kinds of cataclysmics, such that between these stars, this flow of material may become optically thick. Okay? And so it isn't often that I get to do a demonstration, but to illustrate this, let me stop screen sharing for a moment, turn on video, okay? And so I hope you can all see this. This is a common envelope. It happens to be an extremely good scamorza, but it is an optically thick surface, slightly less than 2 solar masses. And as you notice, it is composed of unequal masses. So you have 2 stars now that are overfilling their Roche radius, at least in the kitchen. And although there's no flow here, what you've got, perhaps it would be better if I use this side. What you have is a surface that reaches a constant temperature, a uniform temperature, and I'll get back to that in a moment. As this rotates, you see a change in the surface area. So here you would have a maximum, here you'd have a minimum, a maximum, another minimum, which would be a different magnitude. This is an eclipsing system, okay? And the most important thing is you see that this area has no corners. And so as this rotates, you see a continuous light curve with 2 minima. And those minima happen to be connected with which part of the surface you're seeing. The second thing that's important, and the reason I'm showing you this dynamically using the scamorza, is that here the rotation is such that this side is moving away from you and this is moving towards you. So in the line profile that comes from this photosphere, this side, which is obviously covering more area, is red shifted, and this side is blue shifted. And here, exactly the opposite. So you have a line profile that actually looks like the star. Every portion of this surface, you see that here you have a larger area projected, and here you have a smaller area projected. Okay? So far, so good?
Yeah.
This part, of course, has the highest velocity, as does this side in the opposite direction. And so the line profile actually mimics the shape of the star. And now we'll come back to what I was saying before about the rotating star, because it's the same thing. The profile that results from a rotating stellar surface effectively mimics the shape of the star. It will not look like a Gaussian. It will not look like a Lorentzian. It'll actually be distorted because each part of the surface has a different projected velocity, and different portions of the surface cover different fractions of your field of view. So going back to this, now changing screens. So yes, there it is. So in looking at this, if you happen to be here, then this side and this side are going in opposite directions, and the radial velocity here is that which is projected along this surface. The result is the line profile looks like that, where this is 0 velocity and this is okay. And so this is the effective intensity, where for this star, the shape of the lines will look like this. And in the opposite phase will look like that. Now, The importance of this is that an observational result is behind this affirmation. When you look at the light curve of a W Ursa Majoris, and you also look at the spectrum, that is, this as it varies, there's something very striking, something that we still don't understand. This surface has a constant temperature. This one doesn't. This is a rotating surface. So is this. In fact, this is rotating a hell of a lot faster than it should be if it were, say, a main sequence main sequence, let's say, G star, where if you've got a star at the age of the sun, its rotational velocity is only kilometers per second. Its rotation period is of order a month. These have rotation periods of a day. So you're forcing a star which should otherwise have a completely different structure. Okay. One moment, please. Okay. Okay, we'll just let it ring. So what you're looking at appears to be literally a photosphere. Now, that implies that in this otherwise stationary position of evolution, material optically thick gas is flowing between these stars and also through this neck, which may in fact be very marginally in contact, much less than that scamorza. There's one picture that says this breaks and another one that says it actually stays stationary. This actually isn't important. What is important is that this as a common structure is stable. Okay? That's what I'm trying to emphasize. And this is usually what one talks about when in normal stellar physics, we think about common envelopes. The W Ursa Majoris stars are one class of binaries. They also show dynamos, which means that they actually have some differential rotation, and there are indications of star spots. They show flaring behavior and everything that one would expect for really pathological cases. Their internal structure is very, very different than normal stars in the sense that they have normal luminosities for their masses, but again, that's not what you see. Now, what I want to emphasize is that this is not what we're about to talk about. These systems do not merge, at least not in their lifetime on the main sequence, but they will merge. Eventually, the more massive star, and the mass ratios here are not 1-to-1. They're very often as large as 2-to-1. The more massive star is clearly going to evolve more rapidly. It's going to expand more quickly, and even though that's on something much slower than the thermal timescale, it's still going to be likely that in time, these two are going to englobe each other in a much more extended envelope. If that happens, then there's a possibility of an in-spiral occurring in that this star, the less massive star, can, in the envelope of the other star, feel a drag. Now, again, to put this in some perspective, what we're talking about is the equivalent of a star that has a velocity inside a very dense background. And so it's creating around itself literally a wake. And this turbulent coupling, not unlike the motion of a car, because this is only mildly supersonic at the temperatures that this will eventually reach at the base of the envelope. If the velocities are only say 100 kilometers per second, the temperature at the base of the envelope of the star that's expanding is hotter than that. And so the sound speed, it may actually be higher than the orbital velocity. And so this is actually almost conventional drag. You know that, like with satellites, if the drag slows a satellite down because it's moving through the Earth's atmosphere, this causes a loss of angular momentum, since for Keplerian orbit, the angular momentum is directly linked to the kinetic energy. Okay, it's a bound system. And in this case, since the bulk of the mass is actually still in the core, we can use this argument very simply. The companion star, the lower mass star, starts to inspiral. As it goes deeper, the drag is going to increase, both because the background density increases and because the orbital velocity increases. You know, the usual shtick that when you fall in a gravitational field, you're going faster the closer you get to the ground. Well, it's the same thing here, that the faster the object moves, the more rapidly it's going to spiral into the core. And eventually, something else can happen. This outer, this wake and this bow shock, or this bow wave, eventually can heat the envelope. And drag is a frictional process. So the energy has to go somewhere. And in effect, what's happening is this object that's inspiraling is doing work on the envelope. It's heating it. It's going to cause it to expand. And at the very end, the question of whether this star can actually arrive at the core, or that something else happens that blows the envelope off before the actual fusion occurs, is a complete, right now, an open question. Okay? The only thing we're sure of is that this process is inevitable if you start out with a period shorter than a couple of days, and you start out with stars that are a bit more massive than about a solar mass, that eventually they will go through some process that's similar to this. Now, it depends on when this occurs. If they, for example, start out being farther apart, and maybe the stars have actually gone, at least one of them, has gone through helium core burning, or has built up a sufficient helium core because it was more massive than, say, two solar masses. And by CNO, you've gotten a substantial but chemically distinct core relative to the outer envelope. As the star loses its envelope, it's going to eventually expose the core. And at this, remember, these stars are getting closer together. So as the system shrinks and the ejection of the envelope continues, eventually you can wind up with a system that looks like that, that you have here the former companion. Actually, I'll do it this way. And here you've got a white dwarf, which is the former core. And the period of this thing is going to be less than a day, substantially less than a day, even though you may have started out with a system that was wider. Eventually, because of evolution, you're going to wind up here. In a remarkable and accessible paper through the ADS, Pachynski in 76 just did this thought experiment that I just did with you, of just asking, you got two stars that happen to be living in the same condominium, and they're a little bit too close to each other. And one of them starts to expand. What happens? The reason for that is the apparent paradox that when you look at the distribution of cataclysmic variables, they all have very, very, very short periods. Some is as short as an hour and a half or even an hour, some even less. So you've got a white dwarf and something else that's a sort of main sequence star. And it wasn't just a question of how the hell do you get the white dwarf, but how did you put the star in that system in the first place? If you've got when looking at a helium white dwarf, in effect, there's no problem. You can have a zero 0.6 or zero 0.4 solar mass helium star that helium white dwarf. This started with a star that was maybe a solar mass. And okay, by some magic, it goes through a striptease, and what you're left with is the core. So you got this low mass helium object. Maybe it started out with a period like this, maybe a period of a day, and it kind of stays that way. But there's a different problem if, as we were talking about with novae, the white dwarf is rich in carbon or rich in oxygen or even neon. In other words, that the star in which that core grew had to be much more massive than one that produces the helium core. And consequently, it's also going to be rarer because we know the mass function for the stars. But the more important point is it's going to be bigger, physically bigger, not just more massive. So to build to the point where it's actually been able to synthesize excess carbon and oxygen by alpha processing, that star is going to have gone through the red giant branch. Consequently, if the star is to do that, there's a limit to how close the original system could be. And that was really Pyczynski's point. Starting with this consideration was fine, but the real problem was if you start with a system that's wider, so the stars, like in symbiotics, are evolving almost independently, but they're just that close enough that one of them in its later stage, more massive, is going to engulf the other one. And then you have a completely different in spiral because one of those stars is much more evolved. Its envelope structure is completely different than on the main sequence. It's going to be convective. It's going to have a much more luminous core. And consequently, when you have this in spiral, it's going to be much more violent and much more dramatic because the material that this is now going through is going to be very, very much denser and completely engulfing the system. The idea then is that for some period of time, the system is going to look like this, with much less of a carbuncle here. But this will evolve in time. And that is why I was rotating the Scamorza. You should be able to see this if it happens in real time. So now let's go to the alternative screen. Okay. And now, so there's our system close up. Um, and again, I just want to emphasize that like, well, actually, this even shows star spots, which is rather nice. Um, and, plage regions, and these could even be prominences. Uh, and if you think I'm joking, I'm not. Uh, this actually is really what one of these systems should look like. They're also very tasty. Um, so in 2009, an otherwise relatively uninteresting star that was a variable that was known as a variable from Ogle, did something that was rather unexpected. It, well, you see the scale here, okay? It went from about 16 to 17th magnitude in which it was a variable. Actually, I'll show you that in a minute. And suddenly brightened by 7 magnitudes. Now, you don't expect this kind of behavior from an ordinary binary any more than the line in Ghostbusters. In fact, it got brighter than 10th magnitude in I. This was discovered by accident because in the Ogle photometry from which this was taken, this happens to be in the direction of the galactic bulge. It's in Scorpius. And just by chance, it happened to be in the field that was being monitored for variability and ultimately looking for microlensing gravitational effects. This was clearly not something that was previously expected, but it had been observed, in this case, for something like 8 years beforehand. It had a period of a little less than 1.5 days. And in 2002, that period was seen to be changing. Not in the way that one would expect if you had a mass exchanging binary system. So let me make that clear. In systems like Beta Lyrae or W Serpentis, the ones that are the really extreme algol systems, where one of the stars is filling its Roche lobe, and there's a stream that's going off to the other star and forming an accretion disk. The reason the system changes its period is because of this kind of zero-sum game that you're taking mass from one star and you're dumping it onto the other, so the relative distance between the stars and the center of mass changes, which changes the period. Depending on whether it's the lower or higher mass star that's doing the exchange, the period can increase or decrease. But we know this well. It's something that variable star observers call, it's one of their activities. It's an O minus C diagram, observed minus calculated, where you look at the change in the phasing of the orbital period from one cycle to another. And from that, you can infer that there's been a change in the orbital period, which is usually of order minutes. This wasn't. That between 2002 and 2005, this period changed by almost 1% of a day, and it was accelerating. Now, this is something that indicates that the angular momentum of this system was rapidly being dissipated, and that if this was a Keplerian orbit, the system was actually shrinking and shrinking fast, because you see that from 2006 to 2007, you had the same drop as you had going from 2002 to 2006. Okay? And this continued as the fluctuations show in this light curve. The light curve was this. That is, this is the period between 2002 and 2006. And you see that it looks like a contact binary. This is, Skamortzes in the sky, that there were two minima. There was no spectroscopy available, and this is a faint object. The only reason it could be done was because Ogle was constantly staring, so the amount of data that allowed you to fold onto itself the photometry to get this kind of of quality and signal to noise was incredible. But just take a look at this, because this is what happened later. This is 2007. The light curve was now single. And not long after that, you had the main event. That is, you had a sudden decrease in the brightness in the infrared, and then an enormously rapid increase over a period, in this case, of a mere couple of weeks. Now, when you consider what this means, that you were releasing the luminosity, at least in the infrared, of this object was increasing by more than a factor of 1,000. This implies an enormous source of energy. And in particular, it implies that if what you're seeing in this interval is this suddenly engulfing, one star suddenly engulfing the other, so that you've changed from seeing this constant temperature surface from the two stars to seeing something not just irregular, but a completely different shape. This implies that you're pumping energy into the envelope, and you're doing it from a depth that's completely opaque. So you're literally, and you're inflating the photosphere. And the next step after that was complete expulsion. That this is the sequence immediately after the peak of a couple of the lines from this star, that on the left is the O1 6300, and on the right, the calcium 2 7291, both of which are forbidden transitions, and both of which indicate the presence of very low density gas and moderately low ionization. Both of these sequences were taken with UVIS. This is from work that Ellen Mason and I did a couple of years ago. I just want to emphasize that this is what tells us something about what was going on and the sort of thing that you would be able to observe. This band shows the oxygen 1 line, the 6300, which for most of you is more an annoyance than anything else because it's a line from the atmosphere. The 5577 line is also from the atmosphere, and this is a doublet. So in fact, there are two lines here coming from the same multiplet that are overlaid. Now, the reason I'm showing this is that before we talk about what else the envelope was doing, while the system was still bright, there was something very remarkable in the spectrum. This absorption line. It may not seem like much, but this is a forbidden line. If it were a normal stellar photosphere, you would never be able to see this line except in extremely high resolution observations for a surface with this kind of spectral energy distribution. The line, in fact, is optically thick. And I've got to say, personally, the thing that was striking when I first saw this with Mason is that I had never seen this line in absorption except in the solar spectrum. That it's used as one of those lines to get the oxygen abundance precisely because it's never saturated. In this case, this was against a star whose surface was inflating. This was the clue to what was going on, and I think it's important to emphasize this because the other part of the common envelope, this engulfing phase that you saw in this light curve, This is messy. There's a lot of junk around here that is screwing up the minimum. There must be material that's around the system that you're not seeing so evidently here. In this picture, the argument is that around the system, there's in the equatorial plane and at distances above and below it, there's crap that was ejected in the process of this merger. That, let's put it this way, when the stars are beginning to merge, you're doing work on the envelope. So part of that is going to inflate the optically thick part, that is the photosphere. But remember, atmospheres are fuzzy, and so they're not walls. Above that photosphere, there's a continuous distribution of gas. And that gas is also going to be heated. It's also being driven to expand. It's just not going to be explosive, and it's going to move outward in the plane, preserving angular momentum. So what you're going to wind up with is a kind of donut around the star, or we'll say an expulsion disk, the sort of thing that has been invoked in other systems that I've mentioned when we were talking about luminous blue variables. There are indications in those that you have circumstellar disks. There are also indications for supernovae that, especially for late time interactions, there's circumstellar material around the star that eventually goes into a core collapse. Here, the indication is that we were seeing something around the system that had such high column density that a forbidden line was optically thick. Now, in both of these cases, I should emphasize something. This isn't just any forbidden line. This is from the ground state. So if you see this thing in absorption, you have a direct measure of how much material there is along your line of sight, which you're not going to have from an excited state. For that, you need the temperature. Here you don't. And oxygen, because we didn't have strong hydrogen emission at this stage, oxygen has the peculiarity that its ionization potential is just a little bit above that of hydrogen. And so you can have a neutral phase even if the hydrogen is ionized. And that's important here because it gives us the amount of material, at least the oxygen, that lies between us and the photosphere. Now, excuse me. The other point was that in time, this flipped over into emission. Now, this is something I want to explain in a little bit more detail. So let me go to another screen share and
Il y a un problème. Oh, c'est la commune. Uh,
Okay. No, I'm sorry, I was
okay.
muted. Okay. So you can now see that this is what the object sort of kind of looks like now. And around this, there's the material that was expelled from the atmosphere that eventually piles up as a kind of circumstellar disk. And we're looking this way. So when this central object suddenly becomes luminous, two things happen. First, we see the absorption from this direction, but we're also, because this is a resonance line, going to see from here emission. Now, this is well known. We talked about this for supernovae. This is well known as a phenomenon. If the objects get bright enough, it's called the light echo. The difference is that here, it's not just a light echo in the passive sense, it's in the active sense, because O1, the forbidden line, has an intermediate upper state such that here the energy is zero. And the difference between these is this is 6,300 and this is 6,364. Okay? So this light pulse excites emission. It's a forbidden line. So the emission is going to happen because the density is low enough that it doesn't collisionally de-excite. But there's a delay. That is, we didn't see instantaneously that the emission line appeared. We first had absorption and then we saw emission. And the emission grew until we saw the whole ring emitting. So the first thing that you see is this part in emission, then this, finally the rear side. The result is that here you have a blue shifted absorption, and here you have a red shifted emission. And that's exactly what we saw. So the indications are that in the run up to the system merging, and consequently, this will be true for all such systems, there was material expelled that eventually might be hit by the explosion. The actual merger appears to have gotten probably to the core. Now, I say probably because of something very remarkable about V1309. We haven't seen the star since. It disappeared from the even infrared. It's below 20th magnitude. It can't even be done with VLT. The thing that's striking is the only thing you see from it is an enormously massive ejecta, which can be actually measured in the millimeter and has been by Kaminsky and others at ALMA. And the indication is that the system looked like this, which you've seen before when we were talking about LBVs, that you have whatever the remnant is here, this disk and two lobes that are at high velocity and expand away from it. Okay? This is effectively the same thing that we see in Eta Carina. The reason I'm emphasizing this is what a merger looks like. The most famous example of it is actually this. Oh, I should show you this. This is the result of measuring this with ALMA. You actually do see two lobes. That one side is red shifted, one side is blue shifted. Relative, it's sort of elongated. At this point, there's still a lot of work that needs to be done observing this, as in we'll wait a couple of maybe decades in order to see what this actually looks like. It's much clearer in the silicon monoxide maser that there's very distinctly two different velocities. This normally would have been interpreted as a disk, but as I was showing you, it's much closer and much more reasonable to interpret this in the way we have with novae as some kind of axisymmetric explosion. Now, this is the whole other class of these kinds of objects. We talked about these, the pre-supernova types and the LBVs that show eruptions and then go back into quiescence. These aren't destructive. The supernovae are. And apparently, these objects that are now called intermediate luminosity red transients or intermediate luminosity optical transients or red novae are intermediate between LBVs on the low end and supernovae on the high end, that they can reach absolute magnitudes of -16, which is about a factor of 5 to 10 lower than a typical core collapse supernova. But the point is they show the same phenomenon that we see in the 1309 SCO. This is the distribution of them, that these optical transients occupy a kind of intermediate regime here between supernovae and that is between core, excuse me. So between core collapse supernovae and the luminous blue variables. So here, they show recurrence. This is something we can just leave behind. It has nothing. Well, okay, let me make a nasty crack. You'll often see in the literature that the discussion of the effective temperature as a function of time is used to characterize these objects. As we've emphasized repeatedly, for novae and for supernovae, the concept of effective temperature is meaningless. You're talking about something that's dynamical, that's highly density stratified, that has a velocity field, and that doesn't look like anything remotely resembling a black body. But in this business, people frequently take the photometry, usually the only thing people have for these things, except maybe, fortunately for low resolution spectra, and they fit black body curves. And then say, well, the black body that fits this is 10,000 degrees. What that means is they've got the photometry that would correspond to a black body, except these things don't look like black bodies. Okay. Way you know they don't look like black bodies is take a good look at the spectra here. Okay? These are examples. They're low resolution, but I'm not going to make nasty cracks about that. You get the photometry and spectra you can in this business. This doesn't look anything like a black body at any point. So what you're really talking about there is the characterization of the bolometric luminosity, which is the valuable thing that comes from photometry, not in a band. If you don't have a comprehensive view of the spectrum, the only thing you're windowing is the relative flux distribution in a given bandpass. That can be because of opacity, because of temperature, because of pressure gradients, velocity gradients, or all of the above. Now, this is an unknown. It's a transient Gaia 22 AL zeta, which, as the name implies, was discovered by Gaia. It is from 2022, and this is the AAVSO light curve for it. It was called a nova. It's been published as a nova, and one of the things I want you to notice is the timescales here don't have anything to do with a nova. It's not as it wasn't especially bright. That is, it never got above about 9th magnitude, but it's quite heavily reddened, and we don't know precisely its distance. That's always a problem with systems in eruption with the Gaia data. But the thing that's important is it shows the characteristics that I was just showing you up here for the red novae. That is, these luminous systems. Let me expand here. Okay. These luminous systems go through two peaks. There's the first peak that's the expanding photosphere, and the second peak that's also the result of recombination, and the second peak that's presumed to be the interaction with the environment. We don't know whether that's correct or not. And it's if what we saw in V1309 SCO is any indication, there is no interaction between the expanding blobs and the the expanding blobs that are off of the plane and the circumstellar material. So you've got this annulus of material and these two lobes that are expanding off of it. Whether this will be able to produce the kind of behavior that's seen in red novae is right now anybody's guess. But I just wanted to mention that. Hold on just 1 minute. I apologize for my neighborhood. Some people don't get it.
Steve,
So-
the time axis on this graph we're looking at, is that in days?
Yes.
Thank you.
Yeah, these are the thing that's important about these is unlike often with novae, you have sometimes long periods of observation beforehand, if you're lucky, because this might have been done with HST or with some other survey. The reason that these particular novae, these particular objects have been singled out is because of the observations of NGC 4490 and M101. These are very well known. Um, you'll have to excuse me for a minute. I need to shut the window. Sometimes in this in this world, politics or protests get in the way of doing science, and that appears to be what was going on. Um, so to go back here, I apologize for the fact that this keeps scrolling back to the beginning, but Macs are like that. So uh, the other class of objects that I wanted to mention tonight, because it's starting to get late and I'm probably trying your patience, is the other example of gravitational interaction between two stars. Up to this point, when we've talked about binaries or mass transfer or interactions, it's always been in the context, like just now, of although dynamical, systems that remain bound and go through relatively slow, non-catastrophic evolution in the sense that something survives the event. There's another class, transients that are going to appear in reasonable numbers in the LSST, but unlike the ones I've been talking about so far, they will not be isolated objects. Now, let me explain this. The merging events that I've just been talking about have been seen in the galaxy. The most famous, besides 1309 SCO, was one that brightened in the 1990s, V838 Mon, which is the one that was the poster child for an environmental light echo that everybody knows, that has the the region around it that looks here, that looks a little bit like something Hieronymus Bosch would have put in the sky. Um, okay, so what I mean is this. Okay, this is the other example of what is meant by an environmental light echo. Uh, this is the time sequence from HST beginning in 2001, showing the individual regions, the shells of this environment revealed over time with optical observations, something that looks vaguely biological, practically like a seed pod, but is in fact just the isochrone, that is the constant time surface as we see it from this material. So the stuff that's on the near side, we're seeing in an epoch that's different than that on the far side. And the result is at this time, for example, let's say we're down here looking this way, we're seeing this from a later stage in the evolution of the source than this. And so even if we have a spherical structure around the star, it's going to have different brightness and also different velocities. Now, again, this is the result of, in this case, the ejection. It's pretty clear that before the merger, this system produced something which was much closer to a thick bagel, okay? That clearly this isn't spherical. It just has a circular boundary, that it really is concentrated in some kind of sheet. The details have yet to be modeled, but this is the kind of environment that when the central star eventually explodes as a supernova, because even though it's blown off a considerable part of the envelope, its core was not degenerate. And so it may not, in fact, explode. It may simply have gone through an extreme event in which a large glitch occurred in its nuclear generation, but it still has a future ahead of it of eventually collapsing. And that material that's circumstellar now from that earlier stage is going to be illuminated and collided with, and everything that we were talking about just a moment ago for the evolution of the common envelope. Now, going backward, the other possibility, which we know from the galactic center, is that in the center of a galaxy, center of many galaxies, there's a supermassive black hole. Saying supermassive implies above about 10 to the 5 solar masses. In ours, it's a bit above 10 to the 6th. And in much more extreme cases, in active galaxies and quasars, the mass is at least an order of magnitude higher. The visibility of that object depends on its being fed. Black holes are remarkably quiet little buggers as long as nothing falls into them. But if something happens to come wandering along, there's a good possibility that an interaction can occur. And in fact, that's one of the classes of objects that we now know exist in galactic nuclei. Specifically, what I'll go to now in changing the screen. So if you have a central hole, so a radius that's proportional to its mass, then placing this in a background of stars means that if you have a close encounter, you simply deviate the stars. Or you might expect that you could even have a star that's orbiting the hole at a distance that's sufficiently far that it actually is stable. Okay? Excuse me, a black hole of order 10 to the 6 solar masses is only a bit larger than a couple of solar radii. So, like order of magnitude, a few solar radii. So, you can get pretty bloody close to this thing without actually crossing the event horizon. In other words, you can have very short periods, like around the 10 to the 6 solar mass. You could have something that's sitting at a light day and orbit the hole. And in fact, there is a cluster around our galactic center's black hole, uh, of which one of the stars with the affectionate name S2 orbits with a period of about a day and even shows relativistic effects as it orbits in a very eccentric orbit around the hole. The orbit actually precesses, and the precession is like that of Mercury. That is, it actually feels the deviation from Newtonian gravitation as a result of its orbiting the central object. But it's stable. That is, we've got a binary system consisting of a central massive hole and a relatively ordinary star, in fact, a cluster orbiting it. And there's no problem with that as long as there's no drag. Okay? But you put a black hole in the center of a cluster and imagine something like a globular cluster. The orbits aren't in a particular plane. The individual orbits may practically be radial. And depending on how close you get to the hole, depending on the size of the star and its relative distance, you have the Roche problem that if you get close enough, the star is going to do this and literally start flowing. Now, you're used to this in thinking about a stationary binary system because in that case, if the system is bound, you simply form an accretion disk and eventually everything accretes onto the central object. So you would think, no problem. But if you've got a flyby and this isn't bound, if the velocity is large enough, remember you're outside the event horizon, that in the process of moving past the star, so doing this distorts. And if it gets within its own tidal limit, which just depends on the mass ratio, you're in trouble. The star will start doing exactly what it would normally do if it were in a binary system and filling its Roche lobe. It would start dumping matter onto the companion, in this case, the central black hole. The difference is this doesn't become bound. And if it's close enough, it will get torn apart. That is, enough work will be done on the envelope that it will literally be ripped off. There's no problem with that happening. In fact, we can even make it more efficient if the envelope is convective. So if the star is in, say, the red giant phase and has a deep convective envelope, as you strip mass off, the star expands. It has to do with maintaining the convection and maintaining the difference in the temperature across the envelope. But this is a well-known instability. It was first discussed by Bath back in the 1970s for novae. So you see, everything we've talked about suddenly manifests itself in a very different environment, but it's the same bloody physics that you're taking a self-gravitating blob of gas and putting it in the influence of a companion. The only difference here is that unlike any of the other systems we've talked about, this is unbound. So if this is being unbound, this material doesn't just fly off, it circles. It, in fact, doesn't necessarily even have to collide with itself, but it's going to form a disk eventually around the central object. And that's what is referred to as a tidal disruption event. You'll see X-rays because there will be shocks in the system. You'll see perhaps even high energy emission. We know that the central object in the galaxy periodically flares in the infrared and also in the radio. We also know that it's typical of active galaxies that they go through ejection events, that when you have a radio jet, it's not simply a stationary structure. Periodically, the central object hiccups. And so perhaps some of that is being provoked by these environmental interactions. It doesn't take much to get a star to the point where it is ripped apart, especially if it's already an evolved star. But this is something that we expect to happen in galactic nuclei or in very, very dense systems. It's not something that's going to simply happen in the field. At least we don't think so. But if you had an encounter between a black hole and a star in the galaxy, a black hole like, oh, the one in the SS433 system, it would be a very compact object, only about as large as a neutron star. And the likelihood that you'd have a direct encounter is virtually zero. But you could very easily provoke some kind of an accretion event. They're just going to be very rare. And these tidal interaction events are very rare. They're also very bright. As you'd expect, this is falling into a massive object. So when you actually form this not stationary accretion disk, this is nowhere near steady state. You're going to be releasing all of the angular momentum that the individual pieces falling into this central object have carried, have as kinetic energy. So there'll be spiral shocks, there'll be material blown off, there'll be material blown off in the plane of the system, and this is just a more extreme example of a merger. If you want, it's a merger where one of the stars goes off with a contented smile on its face, having completely consumed the other without leaving a trace. Because eventually this mass is going to cross the event horizon, whatever is left. We could also imagine, and this is one of the things that makes this potentially more interesting for LSST and even for you, is that during the compressional phase that happens during the mass loss, that the core may in fact contract as the envelope expands. If this happens almost in dynamical equilibrium, may trigger a nuclear reaction that goes haywire, that actually goes into a thermonuclear runaway. And this may literally blow itself apart. So it isn't simply that it's losing mass, but the tidal stress may cause the core to undergo a nuclear explosion. These are not, I'll emphasize, these are not frequent events, and they're very specific to their location, but they will show up in large numbers simply because there are a hell of a lot of galaxies in the universe that are accessible to the LSST. If they're bright enough, and some of these can reach 13th or 14th magnitude, you may be able to do some spectroscopic follow-up on them. They're more difficult than any of the other objects we've talked about to date, because since none of these have occurred in our galaxy, when you look at Andromeda, say, at 1 arcsecond resolution, you have a problem that you're looking at something that covers like 20 parsecs with a pixel. If you have M101, you're closer to, say, 50 parsecs. And for any more distant galaxy, the farther away it is, the more of the galaxy you see in your pixel, in your spectrum, as well as the transient that's sitting above it. And the two may be almost the same brightness. So knowing how to remove the underlying galactic background is a real problem with these, much, much more so than with the classical novae and the LBVs and the other systems we've talked about. This pretty much exhausts the class of the most extreme objects. But again, I want to emphasize that all of them share the common feature of radiative transfer. You have dynamical phenomena wildly out of thermodynamic and hydrostatic equilibrium, in which the material that the photosphere that you're observing, and the ejecta and or other structures change optical depth in time differently depending on which lines you're looking at and which portion of the spectrum you're looking at. So you can use all the techniques that we were talking about from the very beginning, simply in a different environment. The physics is identical. It's the setting that's different. One of the things I've been trying to emphasize and will continue to emphasize in our discussions is that the techniques of hydrodynamics and radiative transfer, and especially radiative transfer and the formation of spectra, provide more information than you'll ever be able to get from simply looking at the energy budgets. Without the dynamics, you cannot know what's going on. The only thing you can get is orders of magnitude of what processes might be involved. Once you have the spectrum, you're home free. You have, in this case, even three-dimensional structure because you're doing this in time. It happens that in the galactic center, you can actually resolve the system. But if a tidal merger occurred, if a tidal disruption event occurred in the center of the galaxy, we wouldn't be able to resolve it. We would be able to see its products, as you do for supernova. But everything that is contained in the spectrum in that time series is the dynamics, the geometry, the mass, and ultimately the dynamical energetics, the kinetic energy. And then that coupled with the photometry, with the spectrophotometry, allows you to do everything you're going to need. So at this point, I think I've tried your patience to its limit. I hope at least this was understandable. Um, I hope to this point that I've been able to get across the incredible power of this way of thinking, that you can actually run through in your head the development of a spectrum and then compare that with what you're seeing. And so from that, build up an intuition. You can work at both low and high resolution and get different kinds of information depending on the spectrum quality that you're working with. But once you have a spectrum, all of these possibilities are laid out in front of you. Before we finish, in light of what I just said, there's something that I want to make known. I hope you'll pardon a distinctly political statement. A couple of days ago, it became known that the American administration, the Trump administration, is going to close the atomic division at NIST, which will mean that the NIST database of atomic data and the scientists who were involved with its maintenance and verification, and who themselves are some of the best atomic spectroscopists in the world, are going to be fired, and the division is going to be closed. There's no indication that the database is actually going to survive. We don't know anything about that. The only thing we know is that to this point, every one of these threats has been carried out in the other agencies, and so there's no reason to think that this is just idle chatter. At this point, there have only been what have been well-meaning but completely ineffective reactions on the part of the scientific community. The only well-publicized activity was a petition signed by a large number, something like 1,000 scientists. I signed it also just because of well, it's kind of a moral obligation to do such things, but it's going to mean absolutely nothing. Like, we know this administration doesn't give a damn about anything like the opinion of the scientific community or of the public, as long as it doesn't agree with what the what the petition says. So in this case, many of you are, well, you're all scattered over the globe. We need a quick, concerted pressure on institutions involved with research, especially the IAU, but also the national institutions like the CNR, the CNRS, the INFN, ENAF, uh, to coordinate, and especially the IAU, to take this over. We need a way of preserving this. And so far, no group has stepped up to this. The IAU has been notified. I'm a member of the Council of the Stellar Division. They've been notified. There's been no response. We need action quickly. Otherwise, this resource may disappear the way it has for NOAA and for NIH, and it's not even clear that it's going to ever be recoverable if that happens. Everything that I've been talking about is based on that. All of the atomic and molecular radiative transfer work is based on the linkage between the different databases, the Vienna Atomic Database, NIST, the ExoMol, HITRAN. All of these are vulnerable because they're funded externally or they're maintained by agencies that are part of the government. That's the only comment I'm going to make, but I want you to be aware that we're living, as Francois had said last time, in extremely perilous times for continuing in science and in the kind of work that has produced everything that we've been talking about for these months. So I can't apologize for what the government is currently doing. I'm on another side of the pond, but this is something that you should keep very careful eye on, and perhaps even act in the way that I've been talking about. More than that, I just want to thank you for all of these times, and I hope we will be able to continue. So I'll shut up now. And if there's anything that I can help clarify, or you have any ideas or questions or comments, go for it. Please.
Thank you, Steve. To be clear, I think that if amateurs among us this evening spend so many time in observations, studies of the observations, and so on, it is that really we trust in science and education for the future. That's clear. We need it. I have.
Steve, this is Wayne Green. I've got a question for you.
Please.
There's a couple of really oddball creatures out there, which are things like helium core stars and Wolf-Rayet binarity that we see evidenced in the fluffy stuff that's around the Wolf-Rayet binaries, and where they shed their outer photosphere or their outer envelope, but yet maintain structural integrity on the inside. And the more you venture up in mass, the more frisky these things get. And so there's an element of those kind of stars that I'm sort of interested in, because I think spectrographically, if we look at the variability of the spectrographic signatures, we may see something. It's still a little early days for us to be talking about some of the results that we found. Not that we found any, we're still trying to figure out how to process massive amounts of data. There was another question I had that related to common envelope events. Are you familiar with the work that was done by Ursula DeMarco and her Plan B?
Mhm.
You know, there's a lot of stuff in there about conservation of angular momentum.
Oh,
And
yeah.
then there's another really frisky creature out there. It's called The Bullets of Orion by Bob Odell, Fingers of Orion by John Balley. And that's where we look like we have literally an explosive detonation that has nothing to do with the thermonuclear properties of this thing. Maybe it was an angular momentum spin up where the gravity just became overwhelmed and these things flew apart. Have you dealt with anything in that area?
Yeah.
Okay.
Well, first, it's virtually impossible to spin a star up to the point where it breaks up unless it's luminous enough that it actually produces what is referred to as decretion disk. So yes, the B1 model for the so-called B bracket E stars is that they have extended disk structures that they're very rapidly rotating, and they're sufficiently luminous that they're actually getting a rotating kind of slow wind forming a disk around them. Uh, that's been a picture for these for a long time. They may also be binaries, and the way that you can spin a star up, in fact, this is something I've worked on over the years, is by having an accretion flow. We know this works perfectly for white dwarfs, that in novae you have an internal boundary layer at the inner part of the accretion disk. And because the Keplerian velocity is what the star would have if it broke up, okay? Because the mass would still be there. It simply wouldn't be overwhelmed by the central mass relative to its orbital motion. The spin up of the star gets it to the point where it becomes synchronous with the orbital period. And this isn't a tidal effect. This is actually direct spin up. There's one system that I know among the algols that does this, except it's probably not the whole star that's spun up. In that case, it's U Cephei that has a rotational velocity at the equator of something like 300 kilometers per second. But in that case, and with normal stars that are undergoing accretion, they look like they've been spun up to this ridiculous velocity. But it's more likely that you're just seeing the photosphere spun up and that it's a boundary layer that's optically thick. Now, in the case of the Wolf-Rayet stars, that's different. Virtually all of the WNs are binaries, probably all of them. And they're the ones that are also connected with the LBVs in the so-called Conti picture, where you go from Wolf-Rayets to LBVs through, or rather, you go from the luminous blue variables to the Wolf-Rayet stars, which have lost a considerable amount of their envelopes by way of starting at the OF stars. So it's a massive star sequence. The nucleosynthesis that gets revealed shows that the nitrogen or the oxygen are both overabundant because you've stripped a portion of the envelope and you've also mixed material from the interior. The connection between the WNs and the LBVs is that the luminous blue variables are systematically overabundant in nitrogen. So it appears that they have, if not a common ancestor, a little bit like Australopithecus, uh, they nonetheless come from sort of the same family. and the processes are somehow related to each other. There's a lot more work to do on that. The Wolf-Rayets themselves are wonderfully dynamical objects. They not only show time variable winds, and that's because of their luminosity and because of the velocities of the winds. The winds themselves are not spherical, even though we treat them that way. And we can see that from the line profiles and from the variability. There are ejection events, there are shell events, there are filamentary structures, internal shocks that show up by the emission of X-rays. There are time-dependent filaments that move outward in the spectrum, so they're actually sampling the radial velocity curve. They're just wonderful objects, and Wolf and Rayet were really onto something when they picked up on these things. The WCs, on the other hand, are a lower mass population, and those are the ones that are more closely connected with planetary nebulae. But when we talk about circumstellar nebulae in evolved systems, all you're really talking about is the garbage that's been expelled over the stellar lifetime. And for the massive stars, if it's ejected at velocities before you get to these dynamical winds, if it's from just the kinds of winds you get in the extreme red giant or supergiant phase, that stuff's going to be hanging around for a while. So you'll get an old wind that then gets carved out by the new wind as the star evolves. And also, if it's far enough away, it may contain dust if it was from the asymptotic giant branch phase, which would mean the star had been more than, say, 8 solar masses or so. And in that case, you have a shell, which is seen in the infrared because it's dusty. And then inside of that, you have the planetary nebula. And inside of that, you have the central body, which can be a helium dwarf, or it can be a WC or a WO star. It can be one of the ones you've talked about. A few of the Well, I'll put in a plug for my two favorites. V444 Cygni is a Wolf-Rayet WN, I think it's a WN7 plus an O star in a binary with a period less than a week, in which the wind of the O star and the wind of the Wolf-Rayet star are literally slamming into each other, and they form a shock wave, a standing shock that you can actually see in the ultraviolet, and you can also measure in X-rays. It's a beautiful system. It's also an eclipsing system, and it shows variable profiles depending on which side of the star you're looking at. My other favorite is CQ-CVI, which is also a WN plus an O star, except it's closer. And in that case, the Wolf-Rayet wind literally slams into the surface of the O star. So it's actually suppressing the wind on one side. There are lots of others like this. Some of them form dust. We don't know why, but they appear to have a sufficient amount of carbon that they're able to form small nuclei. They don't seem to go through the polyaromatic hydrocarbon stage. So that may be because these stars are typically seen as hydrogen poor. The other problem with the Wolf-Rayets, I should mention, is that when you talk to theorists who do stellar evolution calculations, like isochrones, they'll tell you that a Wolf-Rayet star is any star that's lost its hydrogen envelope. These are people who have never looked at a spectrum. Okay, Wolf-Rayets have a hell of a lot of hydrogen. They just have helium to hydrogen ratios that indicate that the abundances have gotten screwed up. They certainly are in some way hydrogen deficient, but to say, as you'll hear from some of the evolution types, as I have heard from even colleagues, the Wolf-Rayet stage is the stage when you have the bare helium core. That's nonsense.
Yeah, I
Okay.
agree with that.
Now, the worst part of this is everything I've just told you is phenomenological. We The wonderful thing is we're beginning to learn about how to treat dynamical mass ejection. And once we've got that in the non-explosive environment in which you can actually look at the instabilities that result when the luminosity is high enough that that you're driving these winds, and that the winds are unstable. We've known that since the 1920s when it was actually first predicted by Milne. The existence of internal shocks, of magnetic fields, because we know now that those are present in O stars. They've been detected, finally. They're nowhere near as strong as the AP stars or the BP stars on the main sequence, but it doesn't take much magnetic field to cause real damage when the densities are slow, as they are in these winds. So clearly a part of this has to be magnetic structuring of the winds. And we don't know how to deal with that yet. Uh, Also, these are very dilute media. And so they can't necessarily be treated like fluids. It's not the same thing as a bathtub. So there, there's a lot of observational work that needs to be done. Uh, the observations, I'll emphasize, have to be done at high resolution. I'm not going to equivocate on that. If you're working at a resolution less than about 10,000, it's nice for a hobby, but you're
Yeah,
not going to be producing something that's scientifically valuable, and you're not going to learn much. And the reason is that the structures you're seeing in these winds occupy relatively small fractions of the solid angle of the wind. So you would expect that they'd be narrow, even if they have high velocities and they change over time. The classic example being Gamma Vel, which is the brightest of these in the sky and unfortunately not visible from north of the equator. But that shows that the formation of these internal shocks occupies relatively narrow velocity ranges that if you don't have high enough resolution, like 30 kilometers per second, you're not going to be able to see these. They're going to get washed out. On the other hand, if you can see them, and especially as they propagate outward, you'll be able to trace out the velocity structure of the wind. And that requires relatively high cadence, and the chances that you're going to get time like that on spectrographs like UVIS or X-Shooter, where you would reach these kinds of resolutions or higher, is like nil. Uh,
yeah,
you know, let's put it this way. You think Wolf-Rayets are neat, but you stack those against anybody's type 1, type 2N supernova, and you know who's going to win. So getting time sequences, which is essential for understanding the dynamics, really falls on your shoulders and those like you.
well,
If
we're getting single night observations at about an R of around 2,000, which we're actually getting ready to push that resolution up. But we're R 2000.
which wavelength region are you working in? I hope it's not
We're
alpha.
working from around 30, call it 3,600 to 8,000 or 7,500.
Okay, so you're doing the whole spectrum.
We're doing the whole spectrum.
That's
Okay. There's
okay,
another trick
then
up my
what
sleeve,
you'll-
but there's more to that. But
okay, what you're going to be principally getting is information about the fluctuations in the terminal velocities of the lines.
yeah,
Because you're working in the optical, you got to remember no matter which transition you're looking at, you are not seeing the terminal velocity of the wind.
Yeah.
Okay? You're seeing deeper than that. So by looking at multiple transitions, which you'll then be able to do, even if you have resolutions of 2000, you'll be able to get some broad characterization of the lines. If it's stable as a calibrated spectrum, and I urge you to use standards and not do this, but with normalization.
No. We are definitely using, a secondary experiment for all of this is using A05 stars as standards. The
Are you
reason for
getting-
that is we're in the southern hemisphere.
Are you getting
in-
fluxes?
We're getting fluxes, yes.
So you're doing this as an absolute calibration.
We're doing it as an absolute calibration.
That's the best thing you can be doing.
All right.
Cadence,
It's protracted and it's computationally intensive, but we're doing it.
I can't see that it's that computationally intensive, but
It is when you look at absorption. The AV of these stars is, we're in the southern hemisphere. And I mean, somebody needs to go down there with a vacuum cleaner. There's just so much random dust here and there. We're choosing references that are within a few degrees of our target, but that doesn't necessarily mean anything given the dust lanes and everything else that are in these regions.
wait a minute. Hold it. You don't care. Wait a minute. When I say absolute, I mean you're using you're observing a standard star and you're using its known absolute energy distribution to get the flux, the instantaneous sensitivity of your instrument.
Yes.
It doesn't matter what star you use. It
It
doesn't
kind of does because of the blue-red shift,
No,
because
it
of,
doesn't. It doesn't matter.
okay,
Only thing that matters is that you have an absolute calibration of the CCD plus atmosphere.
Yeah.
And that you're doing it at the same air mass. Doesn't
yes.
have to be at the same reddening. It won't be, in fact. Most of the stars we use as standards are subdwarfs. So they're
Well,
all
the thing is that most of the stars that you use as standards are too dim for us to use.
Oh, I'm talking about using miles.
Please excuse me. I propose that you continue eventually by email exchange.
Okay, that'll be good.
Okay.
I prefer that these sessions are devoted to astrophysics, much more than how getting a spectrum calibration and so on.
Okay, yeah,
I
I
think that
understand
there
that.
are other groups dedicated for that.
Well, our
You
absolute,
understand?
our A05
it's a way of
absolute
I
reference.
hope
reference.
that you understand, Wayne.
Yeah, our A05 reference goes to the veracity of our Wolf-Rayet stars. But I will take this offline with Steve because what I'm looking at is, can I see variability beyond the wind, deeper into the system than the wind? And that's something that Steve and I need to explore in detail outside of this audience.
Yes, I think, yeah.
Okay, thanks, Russell.
If you permit, I share my screen. And in fact, this is a question sent by email by Thierry Midiven, who animates essentially French group dedicated to observation of transients. And they are using essentially photometry with Gaia filters, but also low and very low spectroscopy. And it was about special event, partial tidal disruption, which has been observed a few years ago.
Actually, that was one that I was about.
With a delay of 2,000 days, about.
Here,
He's
Francois.
asking if the prediction, I know that prediction are not very excellent, but times about other objects, but Possibly, a new event could happen in May or August 2025, and is asking the interest of the observation or and also strategy eventually.
Okay, the failed event was an AppJ paper about a year ago by a Chinese group. And I thought I had included it in the list of slides, but apparently I didn't copy it over. The interpretation is that the object actually survived and it's coming around again. There's every reason to think that that's correct. So what? How else can I put this except that we know good examples of it? They're called comets. So in this case, you have a star that's behaving like a comet around a black hole. One would expect that the fact that the mass has changed in the initial tidal interaction isn't going to have a substantial effect on the orbit of the star. So as it's going around, it's getting continually stripped. Yes, we know that there are stars in orbit around the holes. So I would expect that. It's a beautiful observation that it appears that there actually was something that made it by. So yes, it's worth doing. But you got to remember, these are very faint. So you'll have to do this only at low resolution, which means you're losing most of the information.
Yeah.
You're losing the dynamics for the most part. Most of these are being done with not and that is 2.6 meter and larger telescopes.
Of course.
One of the more interesting things, though, is that in all of these, one would expect strong polarimetric signatures. And so eventually, when spectropolarimeters are applied to some of these events, which to date hasn't really been done, it will be very important for elucidating the geometry and opacity sources for these environments.
Thank you, Stephen. Other questions? No, I don't think. So once again, thank you very much. It was a pleasure to discover very new phenomenals, in fact, for me. And
They were all very precious, and
are very, very appreciated.
So I hope you have a very good weekend. By the time we go through another one of these, the American tax season will have passed, and we will have gone through May Day, which seemed like contradictory events. And I just wish the best for all of you, and thank you deeply for participating. It's always a privilege for me.
Thank you very much,
Thank you
Steve.
very much, Steve.
Thank
On
you,
next
Steve.
time, sorry.
Good night.
Yes,
Thank you, Steve,
bye.
and thank you for your participation.